giant star has been burning for millions of years. To our eyes, it would appear calm, a distant white point steady and unchanging. But inside, chaos reigns. Deep in its core, nuclear fusion slams hydrogen atoms together and forges helium. That reaction pushes outward as heat and light. Gravity pulls inward. For its entire life, the star survives by balancing those two relentless forces. Outward pressure resists inward collapse. The battle never ends. In the universe, a star exists only as long as that balance holds. But this star is not just large. It is titanic. It contains at least 20 times the mass of our quiet and familiar sun. It burns through its fuel with a ferocity that makes our sun seem like a candle. The bigger the star, the faster it dies. A star like our sun lives for billions of years. A star 20 times more massive burns through its life in only a few million. Imagine a life so intense that every second is an explosion. That is what we are witnessing now. Inside the star, fusion builds heavier and heavier elements. When hydrogen runs out, the core contracts under its own weight until it becomes hot enough to fuse helium. When helium is gone, carbon fuses, then neon, then oxygen, then silicon. Each step takes place faster than the one before. What took hundreds of thousands of years can suddenly take only months. The star is racing to build iron at its center, and the moment that element appears, the clock reaches its final second. Iron cannot be burned to produce energy. Fusion of iron consumes energy instead of releasing it. The instant the core becomes mostly iron, the outward pressure that has resisted gravity disappears. Gravity finally wins. In the span of a heartbeat, the star's center collapses. The core, once wider than entire planets, falls inward faster than thought. The outer layers, still rushing inward, crash into the collapsing core. The core slams to a stop. A shockwave rebounds. In one moment, the star becomes a supernova. It releases more energy than an entire galaxy for a brief flash of time. The explosion is so bright that if it occurred in our own galaxy and we saw it with our naked eyes, it could outshine the moon. What remains after such a violent death depends entirely on the mass of the core. A less massive star leaves behind a white dwarf, a core of carbon and oxygen so dense that a spoonful would outweigh cars. But the star we are watching was far too large for such a peaceful ending. A white dwarf cannot hold the weight of this corpse. Gravity demands a more extreme outcome. For stars like this, two fates remain. If the collapsed core reaches an unimaginable threshold, gravity crushes it beyond recognition, and space itself caves inward, forming a black hole. A black hole is gravity without mercy, where not even light can escape. But if the core is massive, yet not quite massive enough to cross that final boundary, a different remnant remains. It is something stranger, something so violent, so dense, and so misunderstood that for decades scientists struggled to believe it could exist. This object is a neutron star. Around 1 to 2 suns worth of material has now collapsed into a sphere only as wide as a city. Think of it, the mass of our sun squeezed into something with a diameter of maybe 20 kilometers. The collapse is so absolute that the atoms themselves cannot survive. Electrons and protons are forced together until they become neutrons. The star becomes a single atomic nucleus, scaled up to the size of a world. To truly appreciate what that means, consider this. A teaspoon of neutron star matter would weigh as much as Mount Everest. That is not exaggeration. The density is beyond human imagination. The matter is so tightly packed that if you removed only a fragment the size of a sugar cube, it would outweigh entire mountain ranges. And it is not because of some exotic material. It is because gravity has crushed matter to its fundamental core. This is the universe at its most brutal. Until the instant before collapse, atoms were still atoms. Gravity did not simply crush stone or metal, it crushed the very structure of matter. It broke the familiar world of electrons orbiting a nucleus and compressed the inner building blocks. It transformed ordinary atoms into pure neutrons, jammed together as tightly as nature allows. Imagine holding a piece of matter so dense that it is no longer solid or liquid or gas in any familiar sense. It is something beyond those words. Pure neutron matter. The strongest material the universe can produce without breaking the laws of physics. The neutron star rotates rapidly, often dozens or hundreds of times every second. Conservation of angular momentum forces the rotation to speed up when the star collapses, like a figure skater pulling in her arms to spin faster. Some neutron stars spin so quickly that a point on their surface moves at a significant fraction of the speed of light. But rotation is not the most disturbing part. It is the gravity. The neutron star's gravity is so intense that space curves around it like a whirlpool. Time itself slows near its surface. If you could hover safely beside it and look outward, you would see the universe speed up around you. Seconds would stretch, minutes would distort. Neutron stars are not black holes, yet they are on the edge of that transformation. They are gravity singularities in progress, only a step away from crossing the final border. They are what remains when gravity destroys almost everything but stops just short of destroying space-time. This is only the beginning of understanding what such an object represents. It is the corpse of a star, but it is not dead. It spins. It beams radiation into the universe. It warps space. It crushes matter into a new phase of existence. It is the loudest whisper of gravity before gravity becomes absolute silence. And now, we must ask the question that every physicist feels when they first study neutron stars. What kind of gravity is powerful enough to crush atoms into pure neutrons, yet still stop short of total collapse? We are about to step into the realm where gravity does not just shape worlds, it overwhelms the laws of matter. This is not science fiction. This is what the universe really does. The neutron star hangs in space like a frozen scream. Around it, what remains of the supernova drifts outward, a vast glowing cloud of gas and dust. That expanding shell will eventually seed new stars and planets, but the core that started all this remains compact and unimaginable. One moment it was a giant star larger than 20 suns. The next, it became a sphere no wider than a small city. It has become something so dense that our language and intuition fail. The crust of a neutron star is unlike anything we know. It is not rock, it is not metal. To even call it matter feels misleading. At the surface, gravity presses inward with a force that cannot be compared to anything on Earth. Imagine standing on our planet and feeling the pull of gravity. Now multiply that pull by a number so large that it becomes absurd. 200 billion times the gravity of Earth. That is not a poetic exaggeration. That is the real gravitational strength near the surface of a typical neutron star. You could drop a paperclip from a height of 1 meter and it would strike the surface at nearly half the speed of light. Half the speed of light. Light itself needs only a heartbeat to cross the distance from one side of the star to the other. The neutron star does not allow gentle motion. Every motion is violent. Every fall ends with infinite force. Near the surface, space itself bends so sharply that any object falling toward the star gains a terrifying amount of energy. Gravity does not simply pull, it accelerates. If you tried to approach a neutron star in a spacecraft, even a slight miscalculation would pull you into its grip. Nothing could escape, not by using rocket engines or clever maneuvers. Once too close, the gravitational pull would overpower everything. Yet in all this violence, the neutron star is stable. Not calm, but stable. Something prevents further collapse. Something stops this cosmic corpse from turning into a black hole. That resistance comes from the neutrons themselves. Inside ordinary matter, atoms are mostly empty space. Electrons orbit far from the nucleus. When gravity crushes a massive star, the pressure becomes so intense that electrons are forced into protons. In this process, they transform into neutrons, and a flood of ghostly particles called neutrinos is released. The core becomes one gigantic cluster of neutrons. But neutrons, like electrons, obey a rule described by quantum mechanics. It is called degeneracy pressure. It means that identical particles cannot occupy the same state at the same time. Neutrons resist being pushed closer together. Gravity demands collapse. Quantum rules refuse. For a brief moment, those two forces reach a perfect stalemate. This neutron degeneracy pressure holds up an entire star. Think of it. A rule of quantum mechanics, a law that governs the subatomic realm, is now supporting a sphere that weighs more than our sun. We are witnessing the universe at the boundary between the familiar and the unimaginable. Stars end here. Physics itself bends here. Everything we know about matter changes. The neutron star continues to cool and rotate. Some of them rotate so quickly that if you stood on the surface, you would be spun around several hundred times every second. Of course, no one could survive even a fraction of that. A human body could not even exist on the surface for a moment. Gravity would flatten the body to a film only a few atoms thick. Bones, organs, every cell would be crushed instantly. From far away, neutron stars often appear as pulsars. They emit beams of radiation from their magnetic poles. As they spin, the beams sweep across space like the rotating light of a lighthouse. Each sweep produces a pulse. That pulse repeats. It can repeat with astonishing precision. Some pulses rotate dozens of times every second with timing so perfect that they rival atomic clocks. That precision helped scientists detect gravitational waves. When two neutron stars orbit each other, they emit ripples in space-time that cause the timing of the pulses to shift. The neutron stars quite literally ring space like a bell, but none of that helps us understand the most important truth. A neutron star is what remains when gravity destroys almost everything, yet stops short of consuming space-time itself. It is the final threshold before the universe gives up and forms a black hole. The boundary between these two fates is razor-thin. If the mass of the collapsing star had been only slightly greater, quantum rules would have failed entirely. Gravity would have crushed everything beyond neutrons. Space and time would fold inward. A black hole would be born. That fine line between collapse and obliteration is called the Tolman-Oppenheimer-Volkoff limit. Scientists have calculated its value to be roughly between 2 and 1/2 to 3 times the mass of our Sun. Beyond that limit, nothing can stop collapse. Not neutrons, not matter, not light. But we are not there yet. We are still at the realm of neutron stars. These are not black holes. These are the universe's most violent corpses. They are the final defeated forms of massive stars, held together only by the strange, stubborn rules of quantum physics. This chapter began with an exploding star. It will end with a simple question. If gravity here can crush matter into its deepest possible form, what happens when that gravity becomes even stronger? The neutron star rotates in darkness, the lone survivor of a titanic death. Matter around it drifts outward into the interstellar medium, scattering the ingredients of future stars, future worlds, maybe even future life. And in the center of that silent cloud spins a city-sized sphere of pure neutron matter. It is smaller than most cities on Earth, yet it contains more mass than our Sun. It bends the surrounding space into a deep gravitational well. Time slows within its grasp. Imagine hovering in a spacecraft at a safe distance. The neutron star drifts against the backdrop of space, faint and dim. It is no longer burning with nuclear fire. There is no bright surface, no glowing photosphere. Instead, the light we see comes from heat trapped within its incredibly dense interior. Even hundreds of thousands of years after formation, its surface temperature can reach hundreds of thousands of degrees Celsius. Despite that blazing heat, it appears deceptively small and still, almost fragile. But this is an illusion created by distance. Approach closer, and the true nature of the neutron star becomes undeniable. Space curves, light bends, The star does not merely exist in space, it reshapes space around it. If you tried to orbit too near, your path would become unstable. Any slight deviation, and you would be dragged inward. The star does not need to try. Its gravity does the work. The surface gravity is so powerful that the escape velocity approaches half the speed of light. To leave its surface, you would need a speed so enormous that nothing built by humanity could achieve it. The surface itself is a world without gentle textures. The crust is arranged in bizarre patterns created by intense pressure. Quantum mechanical forces shape matter here. The crust is so strong that if you struck it, the shock would travel through the surface like sound moving through steel. Beneath that, the density increases until atoms are stripped of identity and reduced to neutron-rich matter. Dive deeper, and the pressure increases until neutrons themselves begin to deform and stretch into strange shapes. Scientists sometimes call the strange inner materials nuclear pasta because of the way the neutrons arrange themselves. They can form structures that resemble long strands, flat sheets, or clusters. These are shapes no material on Earth can form. They appear only under pressures so great that the ordinary definition of matter becomes meaningless. Yet the neutron star holds together. It does not collapse further. Quantum mechanics enforces an invisible rule that says no, two neutrons can occupy the same precise state. This degeneracy pressure is not just a concept. It is an active force pushing outward against gravity. Gravity attempts to crush. Quantum rules refuse to allow it. The neutron star spins. If it emits beams of radiation, they sweep across the cosmos. Every rotation sends a pulse into space. To a distant observer, it appears as a precise rhythm, a cosmic heartbeat. Some neutron stars pulse dozens of times per second. Some pulse hundreds of times per second. Each pulse tells the universe I am still here. The star's magnetic field is intense. In some neutron stars, the magnetic field is so powerful that it affects the surrounding vacuum. That is not poetic language. The magnetic field actually influences empty space. Around certain neutron stars, space itself behaves differently, as though reality becomes flexible. Photons, the particles of light, travel through that space, as if through a strange shifting lens. Every discovery we make about neutron stars challenges our understanding. They should not be able to exist. They push the limits of gravity, quantum mechanics, and relativity all at once. Yet there they are, real, solid, measurable. The more we learn, the more impossible they seem. If gravity increases just a little more, beyond a narrow threshold, neutron degeneracy pressure will fail. Quantum rules will surrender. There will be nothing left to resist collapse. The entire mass will shrink beyond the limit of visibility. Space and time will fold inward. A black hole will be born. Nothing escapes a black hole, not even light. The neutron star stands on the edge of that fate. It is a razor-fine balance between existence and collapse, a balance held by the tiniest rules of quantum particles. The neutron star is not a black hole, yet it is only one step away. Think of what this means. Everything familiar about matter depends on the space inside atoms. Remove that space through immense gravitational pressure, and atoms collapse. Once atoms collapse, matter takes on a new form. If collapse continues beyond that, space-time itself fails. The neutron star marks the place where matter and gravity reach an equilibrium so intense that a teaspoon of this material would outweigh mountains. This is the point where physics is no longer a distant theory. It becomes a force that shapes worlds, destroys stars, and bends time. Neutron stars are the wreckage left behind by the most violent cosmic tragedies. They are not gentle lanterns like our sun. They are the universe's burned-out cores, compacted by violence, surrounded by the ghosts of exploded stars. They exist as warnings of what gravity can do when all other forces fail. And yet, in all their death and finality, Neutron stars create new beginnings. The heavy elements scattered during the supernova will drift through space until they gather in new star-forming clouds. Some of those elements will become planets. Some will become oceans. Some will become the iron in blood. We are not separate from these stellar corpses. We exist because they once died. A neutron star is a corpse, yes, but it is a sacred one. The ashes of its explosion become the seeds of worlds. This chapter began with a massive star burning hydrogen. It ends with matter so dense that the boundary between physics and philosophy blurs. Neutron stars show us that gravity can shape not only the fate of matter, but the fate of time and space. The neutron star did not begin as a perfect sphere of impossible matter. It began as a furnace, a colossal heart of fusion. For millions of years, the star held its shape through balance. Outward pressure from nuclear fire resisted the inward pull of gravity. In that balance, atoms lived peaceful lives. Electrons orbited protons, and protons held their place within atomic nuclei. Matter behaved as we are familiar with it, stable, predictable. Then iron appeared in the core. Iron is the end of fusion. You cannot fuse iron and get energy back. The moment iron dominates the core, the nuclear furnace flickers out. The outward pressure vanishes. Gravity notices instantly. In one terrible rush, the core collapses under its own weight. The material that once filled a space larger than planets is now falling inward faster than imagination allows. Inside the collapsing star, heat rises to unimaginable levels. The pressure becomes so intense that the rules of matter begin to change. Atoms are squeezed closer together. Electrons are forced inward toward protons. The collapse becomes so violent that an electron and a proton cannot remain separate. Under normal conditions, these particles repel or interact through the electromagnetic force. But here, gravity overwhelms every other force. Electrons are crushed into protons. In this crushing, a transformation happens. The electron and proton merge to form a neutron. The process expels a tiny ghost-like particle called a neutrino. Neutrinos rarely interact with matter. They pass through entire planets unhindered. But in the heart of a collapsing star, they pour out like a river. Trillions upon trillions stream through the material. They carry away energy, escaping into interstellar space with almost no resistance. If you held out your hand during the birth of a neutron star, a storm of neutrinos would pass through you like wind through trees. You would feel nothing. As the collapse continues, atoms lose their structure. The empty space between the nucleus and the electrons disappears. This space, which seems vast when scaled up to human comparisons, is a luxury gravity will not allow here. It is astonishing to realize that most of what we consider solid matter is composed of emptiness. Table surfaces, stone, flesh, all contain enormous amounts of empty space inside their atoms. But under the unimaginable pressure of a collapsing core, that emptiness cannot survive. Matter is forced into a new arrangement. The star becomes a city-sized atomic nucleus. Neutrons are packed into the smallest volume nature allows. The space between them is squeezed to nearly nothing. For a moment, not long in human terms, but an eternity measured in stellar death, the collapse seems endless. Then something stops it. When neutrons are forced too close together, a rule of quantum physics resists. Neutrons cannot occupy the same exact state. They push back. This neutron degeneracy pressure halts the collapse. Gravity has met its match. The outer layers of the star have not yet noticed the sudden stop. They are still falling inward at incredible speed. When they slam into the core, a shockwave rebounds outward. The star explodes in a supernova. The blast is so bright that an entire galaxy might stand in its shadow. In that explosion, heavy elements are hurled into space. Gold, platinum, elements that will someday collect in dust clouds and form new planets. But inside the leftover core, matter has passed the point of no return. It is not solid or liquid or plasma. It is neutron matter, pure neutron matter. The densest form of matter, allowed by the laws of physics before collapse, becomes unstoppable. At these densities, words fail. Imagine compressing the mass of our sun into a sphere 20 kilometers across. Imagine taking every atom in your body and squeezing the empty space out of it until only the internal contents of the nucleus remain. If a neutron star were the size of a human body would be the size of a grain of sand. The temperature inside the forming neutron star rises to hundreds of billions of degrees Celsius. For comparison, the center of our sun is only about 15 million degrees Celsius. The forming neutron star reaches many thousands of times hotter than that. Pressure and temperature rewrite the laws of matter. At this scale, even the strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei, is stretched to its limit. The forming neutron star is not smooth. It shakes as it settles. The intense magnetic field locks in. The rotation speeds up. In the final instant before stability, the star spins faster and faster until its rotation becomes furious. The conservation of angular momentum requires that as the radius shrinks, the spin rate must increase. It turns like a skater pulling in her arms, but taken to a cosmic extreme. In some neutron stars, one complete rotation takes less time than the blink of an eye. We watch the transformation. A star collapses. Atoms die. The universe becomes something new. With the collapse complete, the neutron star does not glow with fusion. It glows with the heat left over from its creation. Its surface is hotter than any known furnace, but the energy is trapped inside. There is no nuclear fire to refresh it. The neutron star will slowly cool over millions of years, yet its density will remain. Its gravity will not weaken. Its mass will not diminish except by the faintest radiation or interactions with other objects. This object, formed in the crucible of gravitational collapse, is the first real confrontation between matter and the deepest strength of gravity. Here, we see matter in surrender. The atom, that foundational unit of the world, is broken. Gravity has destroyed the structure of the universe we are familiar with. And yet, gravity has not won completely. Not yet. The neutrons resist final collapse. The star is trapped at a threshold held only by the stubbornness of quantum physics. In this balance, we glimpse something extraordinary. The universe is not made of static, simple laws. It is made of battles between forces, between gravity, which tries to compress everything, and quantum mechanics, which refuses to allow identical particles to share the same place. This neutron star exists because those forces are equal, because the universe allows a stalemate. This is where matter is rewritten. This is where atoms are destroyed. The newly formed neutron star settles into existence, but the violence that created it still echoes through its structure. The surface trembles, not as a ripple on water, but as a vibration through matter compressed almost beyond identity. Beneath that surface, layers of neutron-rich material press against one another with a force that defies comprehension. This is not a gentle world. It is a place where gravity rules with absolute authority. The outer crust is only a few meters thick, yet it contains more mass than mountains. In those layers, nuclei exist in strange shapes, stripped of electrons, held in unnatural arrangements. Imagine a world made entirely of atomic cores packed together so tightly that the concept of empty space no longer applies. That is the crust. Beneath it lies a sea of free neutrons, compacted into a density where a spoonful would outweigh entire mountain ranges. There is no space for fluid motion. Everything inside is forced into stillness by pressure alone. The neutron star radiates energy. In the first moments of its birth, the temperature can reach several 100 billion degrees Celsius. That heat bleeds away slowly through the surface, creating a ghostly glow. At great distance, it looks like a tiny ember suspended in blackness. Yet this star, compared to its former brilliance, is dim. There is no fusion, no light from atomic fire. Its heat is the fading memory of collapse. If we imagine hovering at a safe distance, sensors would register the crushing gravity. The slightest nudge of the spacecraft would pull it downward. Even stable orbit becomes something delicate, a razor-thin path around an object that bends space-time into a steep funnel. To describe this gravity, we try to compare it to Earth. But the truth is that comparison fails. Gravity at the surface of a neutron star is not merely stronger. It exists in a different category. If you dropped an object from shoulder height, it would reach the surface in a fraction of a second, already moving at nearly half the speed of light. Nothing on Earth prepares us for physics where the speed of light becomes the limit chosen by gravity itself. Inside the star, neutrons resist further compression. This resistance is not like a spring or a physical shield. It emerges from a law of quantum mechanics. Neutrons obey what physicists call the Pauli exclusion principle, which states that identical particles cannot share the same state. In more familiar terms, it means that neutrons refuse to be stacked exactly on top of each other. Identity itself creates pressure. Gravity is persistent. It tries to compress further. The neutrons push back. The balance feels fragile. In reality, it is absolute. If the star had been slightly more massive, gravity would have crushed the neutrons past this limit. But here, they succeed in holding the line. A neutron star is born from this standoff. Outside, debris from the supernova expands outward. Gas and dust race across light years. Over eons, those materials will form new stars, new planets, and perhaps among them, worlds with oceans and life. We owe our existence to those explosions. Every atom of iron in blood, every atom of calcium in bone, once lived inside an ancient star. Without supernovae, the universe would be hydrogen and helium, cold and uneventful. Life comes from death in the grand cycle of the cosmos. But the neutron star shows a different truth. There are limits even to death. At some point in collapse, matter stops simply being destroyed and takes on a new form. Here, gravity has not merely compressed atoms, it has changed reality. The atom, once considered an indivisible unit, is gone. The space that allowed electrons to orbit has been erased. Electrons and protons have become neutrons. The material is not plasma, not gas, not liquid, not solid. It is neutron matter, the heaviest possible form of matter before the laws of physics give way. If we could drill into its surface, which is an impossible thought, we would find that the deeper we descend, the stranger matter becomes. Neutrons behave not as particles in motion, but as a collective structure. Pressure squeezes them into arrangements that defy chemistry. Words like solid or fluid are insufficient. It is as if matter has been forced to abandon individuality and merge into a continuous sea. While the star cools, it spins. It spins because nothing stopped its rotation during collapse. Before collapse, the star rotated slowly. During collapse, the radius shrank to a tiny fraction of its former size. Conservation of angular momentum demands that the rotations speed up. This simple law turns giant stars into the fastest spinning objects in the universe. Some neutron stars rotate dozens of times every second. Others rotate hundreds of times every second. A point on their surface moves at a significant fraction of the speed of light. This spin has consequences. Radiation escapes from magnetic poles. The beam sweeps through space. If Earth lies in the path, we see a pulse. That pulse repeats with astonishing precision. The timing is so perfect that scientists use these pulses to test the fabric of space-time. Neutron stars serve as cosmic clocks. They are more accurate than the finest instruments humanity has built. Science once debated whether neutron stars could exist at all. Many doubted that nature could produce something so dense and stable. Yet evidence came from pulse after pulse of repeating signals. These signals revealed that the universe had compact stars spinning at predictable intervals, sometimes hundreds of times each second. Only an object with the density and structure of a neutron star could behave that way. We are watching the moment when atoms ceased to exist and something denser took their place. We are witnessing matter in collapse, halted only by a quantum rule that applies to the smallest particles in existence. The neutron star is not a metaphor. It is real. It floats in the void, a warning engraved into space-time itself. The universe has shown how far gravity can push matter before reality breaks. The universe rarely reveals its extremes. Most stars end quietly as white dwarfs. Their collapse stops while atoms remain intact. Neutron stars are different. They are born only from stars massive enough to ignite every possible reserve of fusion, yet not quite massive enough to become black holes. They live in a razor-thin margin, too little mass, and degeneracy pressure from electrons stops the collapse early. Too much mass, and not even neutron pressure can resist gravity. A neutron star exists only when nature threads the needle. In the newly formed neutron star, the energy of collapse is not just thermal. The internal pressure tries to force neutrons into tighter structures. Deeper beneath the crust where pressure increases, neutrons respond by arranging themselves into strange patterns. Scientists have given those patterns names borrowed from food: gnocchi, spaghetti, lasagna. The language sounds playful, but the reality is a record of our inability to describe something so alien. These patterns form because the strong nuclear force and gravity are engaged in constant tension. The strong force tries to hold nucleons together, while gravity tries to push them closer than that force prefers. The shapes are the compromise. Matter here is not static. Every layer obeys different rules. In the outer crust, some atoms retain limited structure. Deeper down, nuclei elongate. They stretch into lines, then sheets, then into branched networks. Beyond that, in the deepest regions, matter becomes uniform neutron fluid. There is no space, no individuality, no atom. For the first time, we encounter material that ignores the familiar categories of solid, liquid, and gas. Neutron matter exists beyond them. It is a new state of matter. The neutron star emits neutrinos for several tens of seconds after birth, a burst so intense that detectors on Earth have occasionally observed them. These neutrinos carry away an enormous amount of energy, allowing the neutron star to settle into equilibrium. Once the neutrino burst ends, the star begins a slow thermal cooling that lasts millions of years. It does not glow from fusion, it glows from stored heat. If you could stand on its surface, you would not see a landscape. There would be no mountains or valleys. The gravity is too intense for uneven terrain. The star is almost perfectly smooth. Any feature, any bump, would be crushed until it became level with the surface. Just as water finds flatness on Earth, matter finds flatness on a neutron star. The surface temperature may still reach hundreds of thousands of degrees Celsius, yet the star appears black. It emits most of its radiation in X-rays and gamma rays, wavelengths invisible to the human eye. From space, instruments like NASA's Neutron Star Interior Composition Explorer observe these signals. Using them, scientists map the structure of the star and measure its mass and radius with extraordinary precision. These measurements help reveal the exact boundary conditions where neutron degeneracy pressure holds or fails. But the neutron star is not an endpoint. It is a question. The universe is asking how far its laws can be pushed before they collapse. The neutron star remains because of neutron degeneracy pressure. This pressure is not like atmospheric pressure or fluid pressure. It has nothing to do with heat. It exists because quantum rules prevent neutrons from occupying the same state. In essence, the universe forbids neutrons from being identical in every way. That prohibition manifests as an outward force that keeps the star from collapsing into a black hole. But even this rule has a limit. If mass increases past a value known as the Tolman-Oppenheimer-Volkoff limit, the outward pressure fails. Neutrons cannot resist further compression. Gravity wins. The star collapses again. The collapse does not stop. It continues until space-time curves into a point where the laws of physics themselves are swallowed. This transition is abrupt. There is no halfway form between neutron star and black hole. One moment, neutron degeneracy holds. The next, it fails entirely. The star crosses a threshold where no structure can exist. Everything that made the star visible disappears. Only a black hole remains. The neutron star reveals the deepest truth about gravity. Gravity is not just a force that holds planets in orbit or keeps our feet on the ground. Gravity can destroy matter. It can crush the atom. It can overpower the strong nuclear force, the most powerful known interaction in the universe. When gravity succeeds, atoms are erased. When gravity wins completely, even light cannot escape. The neutron star stands at the edge of that victory. It is matter's last defense. Here, in this collapsed world, we witness the moment when gravity forces matter into a new state. The neutron star is the last form matter can take before collapse becomes absolute. In this object, physics shows us its limit. Quantum mechanics and relativity confront each other, not in theory, but in reality. The neutron star does not care about our astonishment. It spins, it radiates, it endures. Over millions of years, it cools. It may eventually merge with a companion neutron star. If that happens, the collision will unleash forces powerful enough to create gold and platinum. The universe recycles even this devastation. But at its core, the neutron star remains a monument to destruction. It is the place where gravity broke the atom. The neutron star hangs like a frozen ember in the dark. It is no longer a burning star. It is a relic of unimaginable collapse, a monument to gravity. From far away, it appears calm. Nothing reveals the violence that created it. But approach even a little closer, and the universe begins to behave differently. The pull of gravity near a neutron star is not just stronger than Earth. It is in a completely different realm. Imagine dropping a paperclip from the height of your knee. On Earth, it falls gently. On a neutron star, that same paperclip would strike the surface at nearly 1/2 the speed of light. Half the speed of light, simply by falling. No engines, no rockets, no force except gravity. The fall takes place so fast that movement becomes a blur. If you blink, you miss the beginning and the end. Scientists have estimated that the surface gravity on a neutron star can reach nearly 200 billion times the gravity on Earth. The number strains imagination. You could weigh a feather here, and it would press into the surface with more force than a building on our planet. Even language breaks under the weight of such numbers. We are not comparing one world to another. We are comparing the familiar to something that rules the fabric of space-time itself. Gravity shapes everything near the neutron star. Space-time is no longer flat. It curves into a deep well. Even light is forced to bend around the star. Light normally travels in straight lines, but near this collapsed core, it curves like a river guided by a canyon. If you looked across the neutron star, you might see the distant background of space distorted into strange arcs. Stars behind it could appear warped or duplicated. The neutron star acts as a lens carved from gravity, but gravity does something stranger still. It slows time. Time is not separate from space. According to the theory of relativity, gravity is not a force that pulls objects downward. Gravity is the bending of space-time itself. A neutron star bends space-time so sharply that time runs slower in its presence. Imagine two clocks. One stays far away in deep space. The other moves closer to the neutron star. The farther clock ticks normally. The clock near the star ticks slower. Not because its gears struggle, not because something interferes, but because time itself stretches. If you could hover safely above the neutron star and look outward, you would see the universe speed up. Faraway galaxies would seem to move faster. Time there would feel lighter. Meanwhile, your own seconds would lengthen and thicken. Every moment near the neutron star would last longer. To an outside observer, watching you from a safe distance, you would seem to slow down. Time does not behave the same for everyone. It flows differently depending on gravity. Near Earth, the effect is tiny but measurable. Satellites in orbit carry clocks that tick slightly faster than clocks on Earth. They must be constantly adjusted so that our navigation systems remain accurate. This small difference exists because the satellites experience slightly weaker gravity high above the surface. Near a neutron star, that effect becomes enormous. The difference is no longer measured in fractions of a second. Time here could diverge by minutes or hours compared to distant observers. The star does not just bend space, it bends history. It bends the rate at which reality unfolds. Imagine you are able to stand in a safe orbit around the star, shielded by impossible technology. You look down at the surface. The crust, only a few meters thick, hides the densest matter known. Beneath that crust, neutrons squeeze together so tightly that the concept of empty space has vanished. You watch the star rotate. A tiny beam of energy sweeps from its magnetic pole. Each rotation marks a pulse of time. To you, those pulses might seem slow and steady, but to someone watching from far away, the pulses would arrive faster. Your experience of time is not universal. It depends on how deep you stand in the well of the neutron star's gravity. Every second drags, every moment stretches. At the surface, gravity becomes so strong that atoms cannot exist in familiar form. The electrons that once danced around their nuclei have been crushed out of existence. The star is not solid or liquid or gas. It is something beyond all that. Yet in all that crushing strength, the star holds steady. The slow cooling begins. The star ages. From a distance, you might think millions of years pass. But near the star, the experience could be different. Time slows for whatever lives deep inside a gravitational well. Human minds cannot truly grasp the idea that time itself can change. We think of time as universal, as constant, as something that cannot be altered. Yet in the universe, time is flexible. Gravity decides how fast time flows. Walk toward a neutron star and you walk into thicker time. Walk away and time loosens. This is not speculation. This is not imagination. Observations have proven that strong gravity alters time. Neutron stars are among the strongest clocks in the universe because their gravity stabilizes their rotation. Pulsars, neutron stars that emit sweeping beams of radiation, rotate with absolute precision. Their pulses arrive with such regularity that scientists use them to measure changes in the fabric of space-time. When gravitational waves ripple past Earth, the timing of pulsar signals shifts by almost immeasurable fractions of seconds. The neutron star is a laboratory where the rules of time reveal themselves. It is a clock that uses gravity to mark the passing seconds. It is a mirror that reveals how fragile our understanding of time truly is. And so we ask, if gravity can slow time, bend space, accelerate matter to half the speed of light, and crush atoms into neutrons, what happens to light itself when it tries to escape? Light leaves the neutron star reluctantly. It does not explode outward like light from our sun. It struggles against gravity. The pull of the neutron star is so immense that photons, the particles of light, lose energy simply by trying to escape. Light is normally constant. It does not slow down. It has no mass. Yet here, even light is affected. Imagine releasing a beam of light from the surface of the neutron star. As it travels upward, gravity pulls back on it. Gravity cannot stop light completely, but it can drain energy from it. When light loses energy, its wavelength stretches. That stretching moves the light into the redder end of the spectrum. Scientists call this effect gravitational redshift. It is one of the most powerful confirmations that gravity is not a pull, but a curvature of space-time. Near Earth, gravitational redshift is so small that only precise instruments can detect it. Near a neutron star, the effect is dramatic. Light struggling upward changes color. The higher the gravity, the more energy it loses. If you could stand at a safe distance and watch the neutron star, the light reaching you might be shifted far into invisible wavelengths. It could leave the surface as visible light, but arrive as X-rays or even gamma rays, the most violent form of radiation nature produces. Imagine that for a moment. Light begins as something our eyes could see. By the time it escapes the grip of the neutron star, it becomes radiation that could tear molecules apart. This warping of light is not only vertical. Gravity curves space sideways as well. Light passing close to the neutron star bends along that curve. From some angles, you could see the far side of the star. Space around it is a bowl. Any photon skimming the edge of that bowl arcs inward. If the bowl were a little deeper, if the mass were a little greater, the light would not escape at all. It would spiral inward forever. A neutron star is on the threshold where gravity is strong enough to erase light. It is not a black hole, but it is close, very close. If the star were only a little more massive, the bowl of space-time would deepen until even light could not escape. That boundary is the event horizon of a black hole. As the neutron star rotates, its magnetic field flings charged particles along its magnetic poles. These energetic particles emit radiation in a narrow beam. If the beam sweeps across Earth, we see pulses. The star becomes a pulsar. Pulsars blink with perfect rhythm. Each rotation sends a beam sweeping across the universe. Some complete one rotation every few seconds. Some complete hundreds of rotations every second, faster than anything built by human hands. Imagine a lighthouse spinning so fast that the beam cuts the sky dozens or hundreds of times before you can take a single breath. The timing never falters. Not once. Pulsars are more stable than the atomic clocks that guide our navigation systems. The pulses they emit are so consistent that scientists use them to measure changes in the fabric of space-time itself. When gravitational waves ripple across Earth, those pulses shift ever so slightly. Pulsars are distant clocks revealing the trembling of the universe. Now imagine being close enough that the radiation strikes directly. The beam would not warm your skin. It would vaporize atoms. The energy contained in those beams is immense. They breach distances measured in entire galaxies. When light bends around the neutron star, everything we know about perspective starts to fail. If you could hover near the surface and look outward, you might see your own spacecraft from multiple angles. You might see it wrapped around the star, not because the craft has duplicated, but because gravity has curved the path of light into a loop. Space itself becomes a mirror. The universe hides no illusions here. What you see is real, but that reality is filtered through warped space-time. The neutron star stands just shy of a boundary. A few additional fragments of mass, a slight increase in its core density, and it would cross that boundary. If it gained too much weight through a collision or by absorbing matter from a companion star, nothing could stop collapse. Within moments, it would fall inward, deeper and deeper, until light itself could no longer escape. The crust would vanish. The core would shrink beyond sight. A black hole would appear where the neutron star once turned. Gravity would tighten its grip into absolute silence. But until that moment, every second near the neutron star is a study in warped space-time. Time slows. Light stretches. Space bends. Gravity here has become more than a force. It has become architecture. Gravity on the surface of a neutron star is not just a number written in equations. It has consequences, real consequences. Imagine a human being lowered toward the surface, not touching it, only suspended a short distance above by some impossible machine. The human body contains structure, bones, muscles, fluids, all held together by forces we never question. Gravity on Earth keeps us anchored gently. On the neutron star, gravity does not anchor, it crushes. The moment a person approaches the surface, the difference in gravitational pull between their feet and their head becomes catastrophic. This difference is called a tidal force. On Earth, tidal forces are gentle. They cause ocean tides. On the neutron star, tidal forces are so extreme that they stretch objects into thin columns. The body is pulled downward with more force at the feet than at the head. The force is not subtle. It is not gradual. It acts instantly. Bones would not simply break. They would be torn apart faster than the nervous system could register pain. Muscles would separate. Blood would move downward in a single violent surge. This is not poetic exaggeration. The neutron star does this to anything that comes near. Even metal would distort. Even rock would flow like syrup. The body would stretch into a thin line of atoms, smeared across the surface in less than a second. That stretching effect is called spaghettification. The word sounds humorous. The reality is not. If a spacecraft tried to hover just above the surface, its structure would be strained. Any deviation in position would result in an uncontrolled descent. Engines would provide no rescue. Gravity here does not offer second chances. The ship would fall. The fall would take a sliver of a second. Impact speed would approach 1/2 the speed of light. At that speed, matter does not simply crush. It becomes energy. The spacecraft would compress into the surface with such intensity that it would vaporize into bursts of gamma radiation. Nothing of it would remain. The crust of the neutron star is the hardest material in the universe. It is not hard in the sense of diamond or stone. It is hard because the force holding it together is not molecular bonding. It is nuclear force. The crust is a lattice of neutron-rich material that can withstand pressures billions of times stronger than steel. If you could strike the crust with a hammer, the hammer would shatter. The force of the strike would simply travel through the crust as a vibration, like sound moving through a mountain. Just above the crust, if matter falls toward the star, it releases energy with terrifying efficiency. On Earth, falling from a height converts gravitational potential into motion. On a neutron star, gravitational potential energy is so immense that infalling matter releases energy equal to nuclear reactions. A single grain of dust striking the surface could generate a violent burst of radiation. And yet, despite the crushing gravity and the destruction it inflicts, the neutron star remains strangely elegant. It rotates. Its beam sweeps space. It keeps time. Each rotation is a heartbeat of gravity, a reminder that the universe can create perfect rhythm from chaos. Imagine watching the star from a safe distance, far enough that gravity does not distort time. You set 2 clocks, one near the star, one with you. You wait. Hours pass. When you retrieve the clock near the neutron star, you find that it has ticked fewer seconds than your own. Time has slowed for that clock. Not because of malfunction, because time itself flowed differently. If you returned home after such a journey, you would be younger than those who stayed behind. This is not science fiction. This is the real behavior of space-time near massive objects. Gravity influences time. At neutron star strength, that influence becomes unmistakable. The neutron star marks a place where everyday experience fails. Space turns fluid under gravity. Time stretches. Matter is crushed into a state where atoms no longer exist. The familiar rules that govern the world break, not in theory, but in reality. This star is not a star in the way we understand stars. It is a boundary, a threshold, a point where the universe reveals that the laws we believe to be unbreakable are only temporary agreements. Gravity here has mastered matter, but light still escapes, barely. Time still flows, slowly. The neutron star has pushed every law of physics to its limit, but those laws have not yet surrendered. We end this chapter with a final thought. Gravity has bent time. It has bent space. It has destroyed the atom. But there is one more question. What happens when gravity grows even stronger than this? Light escapes our sun with ease. It bursts from the surface, crosses space, and reaches Earth in about 8 minutes. The journey is direct. Gravity barely slows it. Light behaves as we expect. It travels straight. It arrives unchanged. Our experience with light is based on a calm universe. A neutron star is not calm. Imagine standing at a distance where its gravity does not crush your body or stretch your atoms. Even here, the star looks wrong. Its outline appears sharpened by gravity. Light bends around it. The space behind it seems distorted, as though reality has been warped. But to understand what is happening, you must follow a single photon. A photon begins at the surface of the neutron star. It is emitted from incredibly hot matter under crushing pressure. That photon tries to move outward, trying to leave the gravitational well carved into space-time. It begins its journey with great energy, but gravity stands in its way. Gravity cannot stop light, but it can weaken it. As the photon climbs upward, it loses energy, it stretches, its wavelength elongates. To stretch is to shift its color. The photon is dragged deeper into the red part of the spectrum. This effect is known as gravitational redshift. On Earth, we see redshift when distant galaxies move away from us. The light stretches as the universe expands. But the redshift from a neutron star is not caused by expansion. It is caused by gravity. The photon tries to escape. Gravity tries to pull it back. The result is a change in the light itself. If the photon began as visible light, it might leave the star as a much weaker glow. If it began as ultraviolet, it might arrive as visible. In some neutron stars, the gravity is strong enough that light shifts beyond visible entirely. It becomes X-rays or gamma rays. That means a camera pointed at the neutron star would see only darkness, even though the star glows fiercely. The camera would be blind because the light has been stretched into wavelengths it cannot see. Now picture a star behind the neutron star. You look toward that distant star and something strange happens. The background star appears in the wrong place. Light from the distant star curves around the neutron star, guided by the intense curvature of space-time. You are not seeing an illusion. You are seeing the true shape of gravity. In this moment, the neutron star acts as a lens, focusing light like a massive piece of glass. This phenomenon is called gravitational lensing. Near black holes, this effect can create arcs and rings of light. Neutron stars are close to that level of power. The neutron star twists space into a shape that is difficult to imagine. If space-time were a flat, rubber sheet, a planet would make a shallow dent. A star would make a deeper depression. A neutron star creates a plunge so steep that the sheet nearly folds into itself. The slope is so intense that objects cannot orbit too close. They spiral inward. In the regions just above the surface, the gravitational pull is so strong that space becomes curved enough that a ray of light may bend around the star and return to where it started. It is as though the star attempts to pull the path of light into a circle. Gravity nearly succeeds. If just a little more mass were added, the light would never escape. That would be the birth of a black hole. Think about that threshold. The neutron star does not hide light completely. It only weakens it. The photon escapes, but its energy has been diminished by the struggle. In that moment, we see the difference between a neutron star and a black hole. The neutron star still allows light to exist. Gravity has not yet won. The neutron star emits beams from its magnetic poles. These beams create the pulses that earned such objects the name pulsar. The beam is not light in the sense of calm illumination. It is radiation composed of charged particles and high-energy photons. These beams rotate with the star. If the rotation is aligned correctly with Earth, we see a flash every time the beam sweeps past our line of sight. The interval between flashes can be as stable as the finest atomic clock. Each flash travels across space for thousands of years until it reaches our world and touches our instruments. In the space near the neutron star, those photons in the beam bend with space-time. The path of the radiation curves. The beam itself may appear to tilt or shift when viewed from different angles. Light becomes obedient to the shape of gravity. It moves where space-time tells it to move. From a safe distance, a neutron star seems faint. It does not shine with the brightness of our sun. Its light is swallowed and weakened by gravity, yet its energy, measured at its source, is enormous. Instruments detect X-rays and gamma rays pouring from its surface. It is not a quiet corpse. It is a furnace of trapped heat. But gravity forbids that heat from leaving easily. Time also behaves strangely. If you could drop a perfect clock near the surface, the clock would tick slower. Not because anything mechanical interferes, but because time itself has stretched. A photon escaping upward can serve as a clock. Every oscillation of its wave is a pulse of time. As that wave stretches, the signal slows. Light marks time. Redshift shows that time itself is dilated. Light loses energy. Time slows. Space curves. Here, gravity is no longer simply a force. It has become an architect of reality, and we are still approaching the threshold. The neutron star is not the end of gravity. It is the beginning of something more extreme. If gravity becomes stronger still, it does not only bend light, it begins to trap it. Light does not move freely near a big neutron star. It must climb a cliff of space-time. The deeper the well, the harder the climb. Every photon is born exhausted. Its journey begins from matter compressed until atoms have ceased to exist. The surface from which the photon launches is not solid in any familiar sense. It is a rigid shell of nuclear material where particles are packed together so tightly that no space remains between them. From this world of impossible pressure, light attempts to escape. As the photon moves upward, gravity reaches for it. Gravity does not grab it the way it grabs objects with mass. Instead, gravity curves the space-time through which the photon must travel. The photon must push through stretched time. Time slows near massive objects. Because time slows, the frequency of the photon slows as well. Waves lengthen, the color shifts. Humans see color as a spectrum from blue to red. Higher energy light leans toward blue, lower energy toward red. When a photon struggles against gravity, it loses energy. It stretches. It reddens. That reddening is not a surface effect. It is written into space-time itself. Imagine a single photon leaving the neutron star. In its home environment, it may have enough energy to scorch atoms. But the farther it travels from the star, the weaker it becomes. If it continues long enough, it might reach Earth as something gentle and faint. That journey reflects the relentless nature of gravity. Even massless light is affected by the shape of space-time. Light that moves sideways instead of upward also reveals the power of gravity. In the deep well around the neutron star, space-time curves so sharply that sideways moving photons follow an arc. Light that grazes the star may bend so strongly that it circles around it. If you look toward the neutron star and saw a distant star behind it, you might see that distant star appear in more than one place. The neutron star acts as a lens, bending light like glass does on Earth. Yet there is no lens here. There is only gravity bending space into a funnel. In extreme cases, the bending becomes so pronounced that you could see parts of the neutron star that should be hidden. The backside of the sphere becomes visible because light curves around the surface and emerges toward your eye. You are not looking through the star. You are following the paths of photons that have been guided by warped space-time. In that moment, you are witnessing relativity in action. Everything about the neutron star exists at a threshold. It bends light almost as strongly as a black hole, yet it still permits escape. A black hole allows no escape. It holds light captive beyond an event horizon. A neutron star is just shy of that limit. A little more mass, a little more pressure, and the slope of space-time becomes so steep that no photon can climb out. That last fraction of mass divides a neutron star from a black hole. At the edge of the neutron star's magnetic poles, something else happens. The magnetic field becomes a guide for charged particles. These particles accelerate along magnetic lines and emit beams of radiation. The beams sweep the universe like the searchlight of a cosmic lighthouse. If the beam intersects Earth, scientists detect a pulse. Each pulse arrives with perfect timing. The neutron star rotates with such precision that the interval between pulses remains steady across years. This stability gives scientists a unique window into space-time. When gravitational waves pass through a region of space, they stretch and squeeze space-time itself. The pulses from neutron stars across the sky shift ever so slightly. By studying these shifts, we can detect ripples in space-time from events that occurred hundreds of millions of light-years away. The neutron star does not simply exist, it communicates. Every pulse carries information about the structure of the universe. Every change in that pulse carries information about the movement of space-time. Light leaves the neutron star carrying a story about gravity. Yet even with all of this bending and stretching, the neutron star is still not the ultimate master of light. It sits one step below the final extreme. Gravity here shapes light, warps time, distorts space, but it does not yet erase light completely. The star is a warning of what comes next. If gravity were just a little stronger, every photon born in that crushing environment would fall inward instead of outward. Space would curve so aggressively that the path of light would become a closed loop. A photon would circle endlessly. No light would escape. No information would emerge. Space-time would become a trap, and at that moment, the neutron star would collapse into a black hole. We are standing on the redshift frontier, the last place where light can still fight against gravity. The space around the neutron star is not silent. It vibrates with energy, radiation, and motion. Yet from a distance, the star appears calm, a dim ember on a black canvas. If you could sense gravity the way humans sense temperature, you would feel a pull so immense that it would steal your breath even from thousands of kilometers away. The gravity warps everything, including the paths of photons that leave its surface. Light is not a messenger here. Light is a survivor. Imagine looking directly at the neutron star through a powerful telescope placed in a safe orbit. You expect to see the surface. Instead, you see the sky behind it. The star curves light around itself and reveals regions that should remain hidden. A glowing halo surrounds it. Some of that glow is light that has circled the star. In the most extreme cases, a single photon can orbit the star more than once before escaping into the universe. The photon carries the signature of its struggle. Its wavelength stretches with every loop it makes. It arrives redder and weaker. You are not observing a trick of optics. You are observing the shape of space-time. It becomes clear that a neutron star does not merely sit in the universe. It alters the universe around it. The star creates a well of space-time so steep that all paths tend toward it. Matter does not simply fall. It accelerates in ways that feel impossible. Dust, gas, or stray particles that come near do not arc gently downward. They dive toward the surface. As they fall, they convert gravitational potential energy into motion with terrifying efficiency. Even a grain of sand would hit the surface with such force that it would produce a burst of radiation. Gravity becomes the hammer. Matter becomes the spark. As more material hits the surface, the star heats further. This heat escapes, but never easily. Every photon is taxed for energy on its way out. The star glows in X-rays, the signature of immense heat. The glow is not constant. It flickers. It pulses. The neutron star spins, and if its magnetic field channels energy into beams, the pulses sweep across space. Each pulse marks a rotation. Some neutron stars rotate dozens of times each second. Others rotate hundreds of times. Each rotation drives the beam through space like a blade of light. If your spacecraft were close enough, those beams would not look like gentle pulses. They would feel like flashes of violence. The energy carried by those beams can strip electrons from atoms. If they hit the hull, molecules would break. The star does not radiate warmth. It radiates power. And yet, what makes this place extraordinary is not the violence. It is the boundary. The neutron star exists exactly at the point where light can still escape. Gravity slows time. Gravity stretches space. Gravity drains light of energy. But gravity does not imprison light completely. Not yet. Think of a line drawn in space-time. On one side, photons struggle but survive. On the other, photons fail. That line is not imaginary. It exists. It is the threshold where a neutron star stops being a neutron star. If the star gains just a little more mass, gravity increases. A fraction of additional pressure pushes neutrons past their limit. Neutron degeneracy pressure cannot resist what comes next. Neutrons can no longer hold their structure. They collapse inward. There is no explosion. There is no outward burst. There is only silence as space-time folds. The star does not shrink gradually. It vanishes. The surface disappears. Light cannot leave. The beams stop. The pulses never arrive again. If you were watching the neutron star from a safe orbit and it reached this moment, the star would simply dim and become invisible. One instant, you would see it. The next, nothing. No light, no radiation, no information. Only a region of space where nothing escapes. That moment marks the formation of a black hole. The neutron star is therefore a riddle written in gravity. It tells us that the universe holds a precise limit, a point where the laws that protect matter surrender, a point where time and space no longer behave as partners, but as barriers. Neutron stars sit just short of that point. They exist as a warning. Stand far from the neutron star and you watch a faint glow. Stand closer and time thickens. Stand closer still and even light slows. Every step toward the star feels like walking into deeper water. You feel resistance. Not physical resistance, but resistance from time itself. Seconds lengthen. The universe beyond appears to move faster. The neutron star does not need to speak. Gravity speaks for it. In its presence, the universe reveals that time is not universal, that space is not rigid, and that light is not free. The neutron star proves something profound. Gravity is not just the force that keeps planets in orbit. Gravity can bend the rules of reality. And this star has not even revealed its most terrifying weapon. Gravity can distort matter. But there is another force here, coiled around the neutron star like an invisible serpent. A force capable of tearing electrons from atoms. A force far stronger than gravity on the surface. The neutron star's magnetic field. The neutron star waits in the dark, a dead sun in a shell of impossible matter. Its surface looks smooth, but smooth only in the sense that mountains and valleys cannot survive here. Gravity has pressed everything flat. The crust is harder than anything the universe has ever produced, yet no one can touch it. Nothing built by intelligence or accident can stand on such a world. To stand here is to die in a fraction of a second. Imagine that somehow a human approaches the surface, not touching it, suspended above it. Even at a distance of several meters, the gravity begins to slide every drop of fluid inside the body downward. The difference in gravitational pull between your feet and your head is astronomical. On Earth, this difference barely moves the oceans. Here, it tears flesh. Your bones do not merely break, they elongate. They pull apart like heated sugar stretching into threads. Muscles separate. Organs follow. Blood rushes downward, not as a flow, but as a violent collapse. Spaghettification begins while you are still in the air. Tidal forces are the reason. The closer part of your body is pulled far stronger than the far side. Every centimeter that gets closer to the surface multiplies the force. You are lengthened into a column of atoms. A person becomes a thread. Structures that evolution perfected over billions of years unravel in less than a heartbeat. If you were wearing a pressure suit, reinforced with metals and composites, it would not slow the process. The suit would crumple like soft paper. The strength of steel is meaningless here. Even titanium behaves like clay. The neutron star ignores material strength. It pays attention only to density. Every element surrenders. Your landing craft would not land. It would not skid or break apart. It would simply stop existing as a single object. The moment it dips too close, gravity seizes it. The hull stretches, fractures, and compresses. The craft slams into the surface at nearly 1/2 the speed of light. The energy released in that impact equals the detonation of entire arsenals. The ship becomes a flash of radiation that spreads across the star. Nothing of it remains. Consider the surface beneath all this violence. The neutron star's crust is only a few meters thick, yet it contains more mass than continents. The material is arranged in a lattice of neutrons and compressed nuclei. Scientists call this arrangement nuclear matter. It is harder than diamond and stronger than steel by a factor of billions. A blow from a hammer would do nothing. All the energy of that blow would travel through the crust like a pulse of vibration, ringing across the star like sound through a bell. Beneath the crust is pure neutron fluid. There is no empty space between particles. Matter has been pushed beyond what atoms allow. Nuclei that once floated in oceans of electrons have been stripped down to the barest structure. Deep inside, neutrons move not as individuals, but as a collective wave. The matter behaves like a single extended object. And still the star rotates. The rotation drags space-time around with it. If you hovered in place, you would feel space-time itself trying to pull you along. This effect is known as frame dragging. It means that rotation does not just spin the star, it spins the space around the star. Every motion near the surface becomes violent. Every force becomes absolute. Now imagine the final step. You are lowered slowly until your feet touch the surface. For an instant, you feel contact. In that instant, gravity increases again, not gradually, instantly. Your bones collapse. Your body is compressed into a layer only a few atoms thick. Every structure, complex or simple, is crushed into uniformity. There is no sensation. There is no pain. The nervous system does not have time to react. Conscious thought ends before the signal to scream can leave your brain. To walk on a neutron star is not possible. It is an idea that belongs only to imagination. Humans are fragile. Even planets are fragile here. If Earth could be dropped onto the neutron star, it would impact in silence and vanish into a shallow dent that barely registers. A world that holds oceans and mountains would be nothing more than dust and radiation. The neutron star would not change at all. And yet, after all this destruction, the greatest danger on the neutron star is not the gravity. The greatest danger is the magnetic field. Even gravity steps aside for what is coming. The magnetic field of the neutron star is invisible, yet more dangerous than the gravity that crushes bodies into atoms. It fills space like an unseen storm. Unlike gravity, which pulls evenly in all directions, the magnetic field grabs electrons and tears them away from whatever they belong to. Even at great distances, it exerts power. On Earth, we never think about magnetic fields as threats. They help guide birds and protect us from solar wind. The magnetic field of a neutron star is not gentle guidance, it is dominance. Imagine approaching the neutron star in your impossible spacecraft. You are careful. You stay far enough that gravity does not distort your bones. The view ahead is a tiny sphere suspended in blackness. The surface glows with X-rays, though your eyes cannot see that light. Instruments detect the signals. Your screens are filled with warnings. Not about heat, not about gravity. They warn about magnetism. The magnetic field twists space around the neutron star. Charged particles spiral along the field lines, accelerating to near the speed of light. They do not move freely. They are forced into perfect paths, wrapping around the magnetic poles. These particles strike the surface and create bursts of energy. The neutron star pulses with light no human eye has evolved to see. You feel nothing at first. There is no wind, no sound, no pressure that touches your skin. Then the machines around you begin to react. Anything containing electrical circuits behaves strangely. Screens flicker. Data corrupts. In your pocket, A credit card would be wiped clean. The movement of electrons inside the circuitry becomes chaotic. The magnetic field is rearranging electricity itself, and that is only the beginning. At extremely close distances, the magnetic field of the neutron star becomes powerful enough to tear electrons away from atoms. The atoms that make up your body are normally stable because electrons are bound to their nuclei. On Earth, it takes force or heat to strip those electrons away. Here, the magnetic field does it effortlessly. If you drift too close, your atoms are dismantled, not by crushing, but by separation. The field unravels the electron cloud. Matter is pulled apart into charged fragments. The strangest part is how quiet the process would seem. The body does not feel pulled or crushed. One moment you exist as matter. The next, your atoms are rearranged. The magnetic field at its strongest does something that gravity cannot. It edits chemistry. It decides which atoms remain atoms. It decides which bonds are allowed to exist. If you brought a simple metal object near the star, the object would distort. Electrons would be stripped. The lattice structure of the metal would warp. It would become unstable. It would twist like soft clay even though no physical hands touch it. The shape of matter responds to the shape of the magnetic field lines. Move closer still, and the field becomes strong enough to alter the vacuum of space. Not empty space as humans imagine it, but the fabric of quantum fields that seethe with virtual particles. Under an ordinary magnetic field, space remains space. Under a magnetic field near a neutron star, empty space becomes birefringent. Light traveling through it behaves as if passing through a crystal. The vacuum itself becomes a lens that bends polarization. Space gains structure. It becomes a medium that light must negotiate. This is the threshold at which the neutron star becomes a magnetar. A magnetar possesses a magnetic field stronger than any other object in the cosmos. The strength is so extreme that even the term 1 quadrillion sounds insufficient. 1 quadrillion means 1,000 trillion. A magnetar can possess a magnetic field 1 quadrillion times stronger than the magnetic field of Earth. With that strength, the magnetic field changes from influence to command. It dictates reality. Consider the force on a single electron. Electrons orbit nuclei because the positive charge of the protons draws them inward. But in the magnetic field near a magnetar, a different rule takes control. The magnetic field exerts force on the moving electron. That force becomes strong enough to overwhelm the attraction between electron and nucleus. The electron is ripped away. The atom is undone. The matter becomes fully ionized. All electrons are stripped. All chemistry is erased. Now imagine your body, built of atoms arranged with care by millions of years of evolution. The magnetic field ignores that structure. It pulls apart every molecule. It edits every atom. Bones do not shatter. Muscles do not tear. Instead, your matter becomes a cloud of separated electrons and nuclei. Gravity would crush what remained into the surface. But the magnetic field does not wait for gravity. It performs its erasure instantly. Anything containing data becomes blank. Anything containing electrons becomes stripped. Anything attempting to resist becomes rearranged. The neutron star does not destroy you by touching you. It destroys you by reaching into the core of every atom and deciding that you no longer exist in your present form. Move close enough and even space behaves differently. Vacuum polarization changes the path of light. Photons flip their orientation. For the first time, reality does not feel stable. It feels like something that can be rewritten. At this point, machines fail, materials fail, matter fails. The neutron star has revealed that gravity is not the only danger it carries. The magnetic field is a predator of electrons. It hunts structure. It hunts chemistry. It hunts identity. You realize that walking on a neutron star is not impossible because of crushing gravity alone. It is impossible because every law of matter is rewritten in its presence. You are not just destroyed physically, you are undone conceptually. The neutron star does not care that human minds struggle to imagine these forces. It does not care that our language bends under the weight of what happens here. Gravity crushes, magnetism unravels. Together they create a world where matter itself loses meaning. The surface below is smooth, not because nothing tries to disturb it, but because nothing can. Mountains cannot form when any raised structure collapses instantly. Dirt cannot exist when every atom is stripped and compressed. There is no soil, no atmosphere, only the exposed skeleton of a star's core. Imagine drifting closer than safety allows. You have already passed the distance where electronics fail. Your displays have gone dark. The magnetic field has stripped their memory. You drift anyway, pulled toward the surface by gravity that ignores your intentions. Your engines fight to compensate, but gravity here is not a gentle pull. It is authority. The closer you are, the stronger the pull becomes. Each second multiplies the force. Your muscles tense as the ship trembles. The magnetic field pushes currents through the hull. Wires behave like veins carrying electricity that you did not command. The hull groans. You feel a strange sensation. It is not pressure. It is not weight. It is the faint perception that your body itself is being encouraged to stretch. Your vision blurs for a moment. Not from motion, but because the light in front of you is bending. The star appears sharper than anything you have ever seen. The blackness of space curves around it as though being pulled inward. Space is not empty here. It is a funnel. You see the faint smear of distant stars as their photons bend around the neutron star, following the curves of space-time. Gravity deepens in silence. It does not warn. The distance to the surface collapses without you noticing how. Inside your body, something subtle begins. The magnetic field tugs at electrons, not enough to rip them away yet, but enough to shift them. You feel a sensation that has no earthly comparison. Your nerves begin misfiring, not because they are damaged, but because the magnetic field is influencing the flow of charged particles within them. You are becoming part of the field. Try to raise your hand. It feels heavy, not from gravity, but from interference. Your muscles receive confused signals. Your body cannot decide how to obey you. You expect pain, but there is none yet. Just disorientation. Your body feels both too heavy and too light. Then gravity reminds you that it is here as well. The pull focuses on whichever part of your body is closest to the neutron star. Even a difference of 1 meter between your head and your feet creates a tidal force strong enough to tear muscle away from bone. Your blood rushes downward faster than any heartbeat could compensate. Your limbs begin stretching before you feel the pain that should accompany it. The signal from your nerves travels slower than the destruction. The crushing force squeezes your body flatter with every centimeter of descent. The difference in gravity across your body grows like a rising tide. Your skeleton no longer supports you. Joints pull apart. The connective tissues that once held your form together surrender to the immense pull. Bones do not simply break. They elongate. They split. They vanish into a stream of matter. Then the magnetic field delivers its final blow. Electrons are torn from atoms. Your body becomes ionized. Atoms no longer behave like atoms. You are turning into separated clouds of electrons and atomic nuclei. You are already dead, though your nervous system cannot send that realization to your brain. At the exact moment gravity completes its work, your atoms flatten into a thin smear. The crust beneath you does not register the impact. The surface does not crack or react. The neutron star does not notice you existed. It has absorbed you. Now picture the star not as a place of destruction, but as a machine. It erases anything that comes near. It resets matter to its most compressed state. The surface is a library of what remains after gravity has erased identity. The magnetic field does not care that your body once had chemistry and structure. Gravity does not care that your mind held memories. Between them, they dismantle everything that makes matter familiar. A person cannot walk here. A machine cannot survive here. A thought cannot last here. The neutron star teaches a brutal lesson. At this scale, existence itself is conditional. Matter survives only if the laws of physics allow it. Everything that enters this environment ends not with fire, not with sound, but with silence. For a moment, step back in imagination. Rise away from the neutron star. Watch the surface recede. Gravity loosens its grip. The magnetic field weakens. Your atoms knit back into structure. Your body remembers its shape. It is only at a safe distance that you can reflect on what waited below. The neutron star becomes small once again, a tiny sphere suspended in blackness. You understand now that distance protects not only life, but the very possibility of form. As you drift farther away, a strange thought emerges. The neutron star is not an object. It is an event, a place where the universe reveals that matter has limits, that atoms are temporary, that structure is optional, that identity is fragile. You are leaving, but the star remains unchanged. One question forms quietly in your mind. If gravity and magnetism can rewrite matter at this scale, what happens in places where both are pushed even farther? The answer lies deeper inside the crust, where matter becomes something that should not exist. The neutron star exists already beyond imagination, yet the universe pushes further. Some neutron stars rotate more slowly, some cool more quickly, some remain relatively quiet after formation. But a rare few do something different. They twist their magnetic field until it becomes the most violent magnetic phenomenon known. These neutron stars become magnetars. A magnetar is born when the star's core collapse leaves behind not only enormous gravity, but a magnetic field wound tighter than anything else in existence. The field does not simply surround the star. It erupts from it. It coils around the star like a living force. It reaches out into space with invisible threads of power. If gravity crushes matter, magnetism here rewrites it. The magnetic field of a magnetar is not a gentle influence like the one that guides compasses on Earth. Earth's magnetic field helps protect the planet from charged particles carried by the solar wind. It is weak enough that you do not feel it. A magnetar's magnetic field is strong enough to reshape atoms. At its extreme, the field can reach 1 quadrillion times stronger than the magnetic field on Earth. 1 quadrillion, 1,000 trillion. The human mind cannot truly comprehend the size of that number. It is a quantity that strains language. Imagine floating far away from the magnetar, still outside of immediate danger. Even here, the magnetic field reaches you. Your spacecraft instruments are quietly influenced. Data begins to distort. Screens flicker as electrons inside the circuitry are forced along new paths. The computer does not fail because of heat or impact. It fails because electrons no longer behave as they should. The magnetic field alters electrical current. You check your pockets. A credit card, perfectly safe on Earth, carries magnetic data in its thin stripe. Here, that data would vanish long before you reach the star. At distances of hundreds of thousands of kilometers, the magnetic field of a magnetar can erase digital storage. Identity becomes fragile. Memory becomes unstable. Information can be wiped clean by magnetism alone. Move closer. Your ship vibrates softly, not from engines, from electrons. The closer you come, the stronger the magnetic field becomes. There is no gradual increase. The rise is abrupt. The field begins to act like a sculptor, carving new patterns in anything that contains charge. Metal inside the controls begins to twist as the field forces currents through places no current should travel. Magnetic lines wrap around the neutron star, opening into great arcs above the poles. Charged particles trapped along those arcs spiral in pathways that are beautiful and catastrophic. Then something impossible happens. The magnetic field becomes so strong that it alters empty space itself. Space does not remain neutral. Vacuum polarization changes the behavior of photons. Light entering this region splits into two paths. One path travels faster, the other slower. The vacuum behaves like a crystal. This effect has been predicted for decades. Magnetars confirm it. Matter enduring these conditions is not merely stressed, it is redefined. At stronger distances, electrons are stripped from atoms. At closer distances, the nucleus itself feels distortion. Magnetism becomes a force that competes with the strong nuclear force. The very glue that holds the heart of an atom together finds a rival. Magnetars do not destroy matter through brute collapse as gravity does. They disassemble matter by editing it at the fundamental level. Atoms lose their structure. A human body near this field would not have time to fall toward the surface and be crushed. The atoms would lose their electrons first, leaving only naked nuclei and free electrons drifting apart. And then gravity would take over. Inside the magnetar's crust, matter becomes rigid under pressures billions of times greater than the strength of steel. Neutrons pair and organize into structures that resemble sheets and filaments. This material has been named nuclear pasta. It is the hardest known material in the universe. It exists only where matter has been so compressed that no empty space remains. Imagine watching the magnetar from a safe orbit. It rotates slowly. The magnetic poles are misaligned with its axis of rotation. With each rotation, the magnetic field sweeps across space, dragging charged particles along. The rotation winds the magnetic field tighter, and the field pushes back. When that tension becomes too much, the crust fractures. A starquake erupts. The magnetic field reconfigures itself violently. The rearrangement releases more energy than our sun produces in years. The explosion does not take the form of fire. It takes the form of gamma radiation. The beam travels outward at the speed of light. If such a burst ever struck Earth directly, it could strip our atmosphere and change the surface of the planet forever. Yet the magnetar remains silent in the void, unaware of destruction. Its gravity would kill you instantly. Its magnetism would kill you even faster. And in the deep crust of this impossible object, matter is reshaped into forms that defy physics textbooks. Neutrons, pressed into proximity, adopt patterns that resemble food. Scientists call them gnocchi, spaghetti, lasagna. The names are humorous only because human language has no better option. Deep inside the star, matter becomes the hardest material in existence. Inside the crust of the magnetar, matter stops behaving like anything found elsewhere. Atoms cannot exist here. Their electrons have been stripped away by the magnetic field. Their nuclei are pressed so tightly that they touch. The space that once separated particles simply no longer exists. Pressure and magnetism force matter to arrange itself into patterns that seem almost biological in complexity. These structures form naturally, without guidance, because neutrons seek the lowest energy configuration in an environment where nothing is allowed the luxury of space. Near the upper layers, neutrons cluster into spheres. Scientists call this region gnocchi. Deeper, the pressure increases. Neutrons stretch into long strands. The strands resemble noodles. The name becomes spaghetti. Beneath that layer, neutrons flatten into sheets. These sheets resemble stacked layers of material, like lasagna. The naming sounds playful, but the reality is brutal. These shapes exist because the strong nuclear force and gravity fight each other to a stalemate. Neither wins, so matter freezes into compromise. Nuclear pasta is not metaphor. It is predicted to be the hardest material in the universe. If a human could somehow hold a fragment of it, the fragment would be heavier than mountains and stronger than any structure conceived by engineering. No tool on Earth could cut it. No force on Earth could dent it. It exists only because the magnetar's gravity and magnetic field squeeze matter beyond what atoms can tolerate. The crust of the star is a mosaic of these neutron structures, fused into a seamless shell that never cracks except in disaster. When the crust does crack, the fracture unleashes energy on a scale that defies comprehension. On Earth, earthquakes release energy stored in shifting plates. On a magnetar, starquakes release the tension of the magnetic field itself. The crust resists the stress until the field twists so violently that something must give way. When that moment arrives, the crust snaps. The star's rotation jerks. The magnetic field reconnects in a new configuration. The sudden change hurls gamma radiation across space. It happens in a fraction of a heartbeat. Space itself seems to flinch. One such burst was detected from a magnetar in the constellation Sagitta. Telescopes around Earth registered a spike of energy so overpowering that it saturated detectors, even though the star was thousands of light years away. For one brief instant, the burst outshone every other source of gamma radiation in the sky. Had that burst been directed at Earth, our atmosphere would have been scorched, and life on the surface would have been altered forever. And that was from a star smaller than a city. Magnetars do not glow like ordinary stars. They do not shine with visible light. They radiate X-rays and gamma rays. They signal their existence only through pulses and bursts. They cannot be seen with human eyes. They must be detected by instruments capable of sensing invisible violence. Gravity crushes matter. The magnetic field edits it. Together, they create a world where matter takes forms that should not exist. Imagine lowering a robotic probe toward the surface. The probe is built of reinforced alloys, engineered to survive the crushing pressures of gas giant atmospheres. It descends. The magnetic field begins to influence its circuits. Data corrupts. Motors misfire. The probe becomes confused. Its systems try to correct themselves, but they no longer understand the commands they receive. The magnetic field forces currents through pathways that were never designed to carry them. Panels distort. Bolts twist. The probe begins to unravel before it even touches the surface. Then gravity asserts itself. The probe falls faster. It does not crash. It is drawn inward. The legs of the probe elongate. The chassis stretches. The entire structure becomes a smear of matter. For a moment, the probe still exists, but only as raw material. It becomes part of the neutron star's crust. The magnetar does not react. It does not flare or tremble. It absorbs the probe as though it never existed. At the surface, beneath the crushing gravity, beneath the reality-bending magnetic field, beneath the crust of nuclear pasta, matter has reached a boundary. It cannot be compressed any further without collapsing into something else, something that does not allow light to escape, something that no longer has a surface, something that no longer has identity. Magnetars show us that gravity is not the only path toward annihilation. They reveal that order in matter is fragile. Identity is fragile. Structure is fragile. Even the familiar concept of space becomes negotiable. And deep within the crust, matter waits at its limit. One question remains. If gravity continues to increase, can even neutron matter survive? The magnetar is a paradox. It is small enough to fit inside a city, yet massive enough to outweigh an entire sun. It crushes matter into a form that nature never allows anywhere else. The moment you cross the invisible boundary that separates ordinary space from magnetar space, rules change. Electrons are stripped away. Atoms disassemble. Neutrons pack into structures that defy every category humans use for matter. We call those structures nuclear pasta. The name sounds humorous, almost soft. Yet nothing softer has ever been farther from the truth. Nuclear pasta is the hardest material ever predicted to exist. Imagine descending into the crust of a magnetar, moving downward through a place that does not know the meaning of distance. The surface beneath you is smooth, but not because erosion has polished it. It is smooth because nothing can stand against the gravity that rules here. Anything that rises above the surface is crushed flat. Any irregularity is erased. The crust feels as though it were carved from a single piece of unbreakable material. You descend deeper. Pressure increases not gradually, but brutally. Nuclei are forced together. Electrons have already been torn away by the magnetic field. Their absence means there are no orbitals, no chemical bonds, no familiar arrangement of atoms. Neutrons now carry the burden of structure. They do not simply pack together. They organize. They arrange into shapes based on the strong nuclear force. Particles that once lived with space between them now exist shoulder to shoulder. At the outermost layer of the crust, neutrons cluster into tight spheres. This is the first stage of nuclear pasta. Scientists call this phase gnocchi. Tiny spheres, pressed into a grid so dense that there is no room for waste. Each sphere is a nucleus pushed to its absolute limit. The density here equals the mass of mountains packed into pieces the size of dust grains. If you could hold a pinch of gnocchi matter, it would outweigh skyscrapers. Drop it on Earth and it would fall through the planet as though Earth were made of air. You push deeper. Pressure grows. Spheres are no longer the most efficient structure. Neutrons stretch into long cylinders. The formation resembles strands of noodles. This is spaghetti. The shape is not chosen randomly. Neutrons arrange this way because the strong nuclear force is short range. Neutrons want to be close, but not too close. Gravity pushes inward. Nuclear repulsion pushes outward. Spaghetti is the compromise. Continue downward. The pressure becomes unimaginable. Individual strands no longer remain stable. Neutrons flatten into wide sheets. Layer upon layer, they stack like the layers of lasagna. The sheets extend through vast regions within the crust. If you could observe them closely, they would look like the architecture of an alien city. Geometry born from force. One more step downward, and we pass the deepest layer. Neutrons stop forming shapes. They lose individuality. They merge into a sea of uniform matter. There is no structure, no boundary, no division. This is neutron superfluid, a quantum ocean, a place where matter flows with zero resistance. If you dropped a pebble into that ocean, if such a thing were possible, the ripple would circle the star forever. Energy cannot dissipate in a superfluid. Within these layers, nuclear pasta forms the strongest material ever discovered. Not strong in the way steel is strong, not hard in the way diamond is hard. Steel resists by distributing force between tightly bound atoms. Diamond resists by locking electrons into rigid lattices. Nuclear pasta resists by using the strong nuclear force itself. No hammer, no pressure, no temperature on Earth could break it. Only a magnetar can make it, and only a magnetar can destroy it. Scientists calculate that nuclear pasta is billions of times stronger than steel. If a mountain-sized block of nuclear pasta appeared on Earth, no machine could crush it, and no weapon could shatter it. The planet beneath it would deform first. The Earth would bend. Yet this strongest of all materials lies beneath the surface of a star that can erase worlds with a single rotation. Nuclear pasta is not decoration. It is a skeleton that keeps the magnetar from collapsing into a black hole. It holds back gravity with the strongest force in the cosmos. If it were any weaker, the star would continue collapsing and vanish from reality. Consider the scale of forces. The strong nuclear force holds the heart of each atom together. Gravity here tries to defeat that force. Where the two forces reach a standoff, nuclear pasta appears. It is not simply matter in an exotic state. It is the physical evidence of a cosmic war between the strongest force inside the atom and the relentless crush of gravity. The neutron star does not know that its crust contains the strongest material in the universe. It does not know that its interior has become a quantum ocean. The magnetar simply exists. It spins. It pulses. It continues to be the most dangerous object anywhere outside a black hole. And this is where the universe becomes philosophical. Nuclear pasta is the last form matter can take before collapsing entirely. It represents a limit, a rule, a point beyond which matter cannot defend itself. One more increase in mass, one more push of gravity, and neutrons will lose. The star will collapse further, not into harder material, but into nothing. No surface, no structure, no escape. The neutron star will cross the final threshold. It will become a black hole. Nuclear pasta exists as the last possible geometry of matter. When the universe squeezes an atom, the atom surrenders its electrons. When the universe squeezes a nucleus, the nucleus surrenders its symmetry. When the universe squeezes neutrons, even they attempt structure, but beneath the final layer of nuclear pasta, when neutrons merge into a superfluid sea, matter finally stops resisting. There is no shape left to offer. There is only density. Imagine being inside this star, not falling or being crushed, but simply observing the interior as a ghost with no mass and no body. Around you, the crust of nuclear pasta forms vast continents. Sheets of lasagna stretch for kilometers in every direction. Below it, the neutron superfluid glows faintly with heat. It is not heat like a flame. It is heat held by quantum pressure. The superfluid does not boil or churn. It moves in silent currents. It flows through the star-like thought. Inside this place, you witness something that cannot happen in ordinary matter. Neutrons pair into a state that allows them to move without friction. They form a quantum condensate. This means they flow with no resistance, no loss of energy, no degradation. If a wave is created within that fluid, the wave continues forever. It never fades. Energy has nowhere to go. The superfluid becomes a memory that the star cannot erase. Yet even here, the magnetic field reaches deep. It threads through the crust and enters the superfluid below. It twists. It strains. It stores energy like a coil wound too tight. The field is trapped within the matter. It waits for release. When the coils of the magnetic field reorganize, the crust fractures. Starquakes erupt. The force of this rearrangement travels through the neutron superfluid with no loss. Entire regions of the crust shift by just a few centimeters. Yet that movement releases more energy than our sun emits in years. Nuclear pasta does not break easily. It does not yield. It holds until the magnetic field reaches its limit. When the crust finally snaps, the release is instantaneous. It is not a rumble or a crack. It is an explosion of radiation. Space itself stiffens around the burst. Gamma rays cross the void in beams of invisible fury. If such a burst hit Earth directly, the atmosphere would be torn away. Oceans would evaporate. Life would end before it could understand the cause. The crust then seals itself again. The fracture disappears. The magnetar returns to its silent rotation. The star is unchanged. Only the universe around it bears the scars. The deeper you go into the star, the more time loses meaning. Above, where the magnetic field scrambles electrons, time still follows a rhythm, though slowed by gravity. Below, where nuclear pasta rules, time seems to thicken. The neutron superfluid carries waves that do not fade. Vibrations become permanent. The star remembers every quake. Matter tries to hold shape. Gravity tries to erase it. In that balance, the crust remains stable. But this stability exists only because the star has not grown too massive. Add just a little more mass, and the balance shifts. At a certain point, called the Tolman-Oppenheimer-Volkoff limit, neutron degeneracy pressure fails. This pressure is not like pressure inside a balloon or inside a hydraulic system. It is a quantum rule. It exists because neutrons refuse to occupy the same state. They resist compression because the universe forbids identical particles from sharing identical configurations. This rule is powerful. It is the only reason neutron stars exist. But every rule has a limit. When the mass of the star pushes beyond the Tolman-Oppenheimer-Volkoff boundary, the neutrons can no longer resist. They have run out of ways to arrange themselves. Nuclear pasta is the final structure they can adopt. When even that fails, gravity claims victory. Neutrons collapse. There is no intermediary state. The collapse is sudden, silent, absolute. The surface disappears. Light disappears. Time disappears. The neutron star becomes a black hole. A black hole is not a place, it is a boundary, a region of space-time where gravity no longer allows information to leave. The star does not implode into something solid, it implodes into the curvature of space-time. The mass remains, but the matter no longer exists as matter. In that final moment, nuclear pasta surrenders. The strongest material in the universe loses to gravity. Matter loses. The universe changes shape. And everything that once was a star becomes a shadow in space-time, where even photons fail to escape. The final truth is this. Nuclear pasta is not an oddity. It is a warning. It shows us how far matter can go before it stops being matter. It shows the exact point where the universe draws a line and says, no further. Beyond this line is collapse. Beyond this line is darkness. Beyond this line is the end of form. If you are ready, we will cross that line. A neutron star is already beyond the limits of matter. It is the remnant of a star that once burned with fusion, radiating energy across light years. Now, all that remains is a core so dense that atoms no longer exist. Electrons have been forced into protons, creating neutrons. The result is a sphere no larger than a city, yet with more mass than 1 or 2 suns squeezed into it. It should not be able to hold itself together. And yet, it does. But there is a final boundary, a point beyond which even neutrons cannot resist gravity. The universe set that threshold with astonishing precision. It is called the Tolman-Oppenheimer-Volkoff limit. It defines the maximum mass a neutron star can possess while still resisting collapse. The number is somewhere between roughly 2.2 and 2.5 times the mass of the Sun. Scientists refine that number with new measurements, new observations, new equations of state for neutron matter, but the conclusion remains unchanged. Beyond that limit, neutron degeneracy pressure, the quantum rule that keeps neutrons from occupying the same state, fails. Gravity wins. To understand what that means, imagine adding mass to a neutron star. Perhaps the neutron star has a companion star. Over time, it pulls gas from the companion. That gas falls onto the neutron star, releasing energy as it impacts the crust. Each collision adds mass. Slowly, invisibly, the neutron star grows heavier. Or perhaps 2 neutron stars spiral toward each other, losing orbital energy through the emission of gravitational waves. The stars approach. The waves ripple through space-time. Eventually, the 2 stars merge. Their combined mass exceeds the threshold. At first, nothing happens on the surface. The star looks unchanged. It continues to rotate. It continues to emit beams of energy from its poles. It appears stable. But deep inside the crust, where nuclear pasta holds matter in its strongest possible structure, the neutrons feel the shift. The inward pull grows stronger than their resistance. The strong nuclear force and neutron degeneracy pressure combine to hold them apart. But gravity increases without mercy. Inside the superfluid core, pressure mounts. Neutrons begin to overlap. They begin to run out of possible states. The quantum rules that once held them steady, the rules that forbid identical particles from sharing the same configuration, reach their limit. Every neutron already occupies every available state allowed by physics. There are no more options. The universe has run out of ways to arrange matter. At that exact moment, collapse begins. There is no warning, no sound, no tremor. The crust does not crack the way it did when magnetic energy released starquakes. Instead, the crust loses meaning. The boundary between crust and core disappears. The pressure exceeds the strength of the strong nuclear force. The lattice that took the shape of noodles and sheets unravels in an instant. Matter stops being matter. The collapse is not slow. It is not dramatic. It is not explosive. It is silent. The star falls inward faster than any signal can escape. Gravity overtakes the quantum forces that held neutrons apart. There is no intermediary form between neutron matter and whatever comes next. There is only absolute surrender. The radius of the entire star shrinks, shrinking again, shrinking until the surface crosses a boundary in space-time. That boundary is not made of matter. It is not a crust. It is not a physical wall. It is a mathematical line known as the event horizon. Once the collapsing surface crosses the event horizon, not even light can escape. Outside, observers will never see the collapse finish. Instead, they will see the neutron star appear to slow. Its pulses will stretch. Its light will redden. It will seem to freeze in time. The last photons struggle outward, losing energy as they climb against gravity. Time dilation becomes extreme. The collapse continues, but from the outside it looks like the star is caught between existence and disappearance. Inside, there is no pause. The collapse completes in a fraction of a second. Atoms have already been destroyed. Neutrons have already been compacted. Now even neutrons cease to exist as independent particles. Matter becomes something that no experiment on Earth can reproduce. The collapse continues until gravity curves space-time so sharply that no path leads outward. The mass remains, but space around it becomes a well with no bottom. The neutron star, once a beacon of extreme physics, becomes a black hole. A black hole is not an object. It is an absence, a region where escape is impossible, a place where every path curves inward, a boundary where time and space trade roles. Outside, space is the dimension that stretches. Inside, time takes that burden. Inside, every direction leads to the center. There is no surface, no matter, no light, only gravity. Imagine standing at a safe distance after the collapse, watching the neutron star vanish. One moment pulses arrive. The next moment, nothing. The pulses stop. The beam of radiation ceases. The star that once pushed the laws of physics to their limit falls silent. All information about the inner structure of the star becomes inaccessible. It is not destroyed. It is hidden by space-time. Inside the event horizon, matter continues to fall inward. Gravity compresses it further. The mathematics describing this interior predicts something called a singularity, a place where density becomes infinite, a place where the laws of physics break. Our equations fail, our understanding stops. Relativity and quantum mechanics clash in ways that reveal how incomplete our knowledge truly is. The neutron star was the last place in the universe where matter still had form. Now that form has been erased. The most extreme forces in the universe have spoken. The strong nuclear force was defeated. Neutron degeneracy pressure surrendered. Matter crossed the line. Gravity took everything. And in that surrender, space-time itself became the cage. If you are ready, we will follow the next evolution of gravity. We will watch two neutron stars spiral toward each other until space and time ripple from the violence. Two neutron stars orbit each other in silence. They were once massive suns, each burning with fusion, each holding planets and storms and light. Now they are corpses, dense as memory and violent as collapse. They orbit so close that space itself twists. Each star pulls on the other with enough force to distort their shapes. They are no longer perfect spheres. They stretch into teardrops, each pointing toward the other. Their final dance has begun. With every rotation, they lose energy. They do not slow. They fall. The loss of energy comes not through heat or radiation, but through ripples in space-time itself. The stars emit gravitational waves. These waves carry away orbital energy into the universe. The two stars inch closer over millions of years, then thousands, then hundreds, then seconds. Their spiral tightens. They rotate faster. Their motion accelerates until each star orbits the other many times in a single heartbeat. The universe does not hear this motion, but space feels it. Humans on Earth built detectors to listen to such events. Those instruments use lasers to measure the stretching and squeezing of space-time. In the year 2017, scientists witnessed the signal of two neutron stars spiraling together. They named that event gravitational wave 170817. The signal did not come from light, it came from space-time. The detectors recorded a faint chirp, a rising note, a whisper of two collapsed stars hurtling toward each other. Far across the cosmos, those stars completed their spiral. Each revolution flings gravitational waves outward in all directions. These waves do not move through space the way sound moves through air. They are vibrations of space. They stretch the geometry of the universe. If you could see them, they would look like ripples spreading across a pond. Each ripple confirms that gravity is not a force. It is the bending of space-time. The neutron stars are close now, close enough that tidal forces distort their crusts. Nuclear pasta bends. The strongest material in the universe groans as gravitational stress climbs. The crust cannot hold. Fractures propagate across the surface. The stars tremble. The rotation quickens. In their final orbit, they spin around each other many times per second. They are smaller than cities, yet heavier than suns, and now they are dancing on the edge of destruction. Their collapse is sudden. The two stars touch, the crusts collide, and matter that has been compressed for millions of years is flung outward in streams. It does not drift, it erupts. Neutrons, free from confinement, combine with heavy nuclei. In the violence of that collision, the universe begins a kind of alchemy. This is the forge in which heavy elements are born. Gold, platinum, uranium, rare on Earth, common only in death. The collision becomes a kilonova, a flare brighter than entire galaxies. Light surges outward. The flash is ultraviolet and blue and invisible to the human eye. Yet its power is undeniable. Even from far distances, telescopes detect the glow. Space-based observatories sense gamma radiation. Atmosphere-based telescopes detect visible light. Radio dishes detect the expanding shell of debris. For the first time in history, humanity sees a cosmic event, not just with eyes, but with instruments tuned to gravitational waves. Observatories around Earth swing toward the location. They detect heavy elements in the expanding cloud. Gold forms where neutron matter is torn apart. Platinum forms. Rare elements that planets crave are released into the void. The periodic table of Earth is written in the language of destroyed stars. The neutron stars were not silent. They created. The collision is not chaos. It is transformation. It is the only known place where the rapid neutron capture process can occur. Neutrons flood atomic nuclei so quickly that atoms jump through the periodic table. Flames of elemental birth spread across space. Dust from the explosion cools. Each grain contains heavy elements. Over millions of years, those grains drift through galaxies. They collect in clouds of gas that will form new stars and planets. Some of that dust falls into future worlds. Some finds soil. Some finds rings on human hands. Every piece of gold on Earth began inside the destruction of a neutron star. The kilonova dims, the fire fades, the heavy elements drift. At the center, gravity finishes its work. The merged mass of the neutron stars crosses the final threshold. Neutrons can no longer resist. The collapse continues until space-time curves into a trap. A black hole forms. The cores of dead stars give birth to something that is no longer matter. The remaining debris continues to spiral into the new black hole, releasing the last bursts of energy. The gravitational waves fade into silence. The universe returns to emptiness. But it is changed. Every neutron star collision spreads seed material across galaxies. The heavy elements formed here enter new stars, new planets, new chemistry. Without these collisions, there would be no gold, no platinum, no uranium, no rare materials for technology, for biology, for civilization. The iron in blood came from ordinary supernovae. The gold in wedding bands came from neutron stars. If you could stand far away and watch the end, the sky would brighten, then dim, then fall silent. What remains is only memory in space-time. The black hole spins. The gravitational waves fade. The universe swallows the last trace of their existence. Two dead stars destroyed themselves, and from their destruction came creation. Matter was crushed, neutrons collapsed. Gravity wrote a new chapter. If you are ready, we will close the journey in the final chapter, where physics reaches its absolute limit and knowledge stops. The neutron star was never just an object, it was a boundary, a place where matter pushed against the deepest rules of existence. Electrons resisted collapse. Gravity crushed them. Neutrons resisted collapse. Gravity crushed them. Nuclear pasta forged itself from the strongest force in nature, and even that surrendered in the end. The neutron star shows us the last place in the universe where matter still has structure. Beyond that point lies only gravity. And yet, we are not finished. There is one final lesson. Neutron stars reveal something profound. They show where the universe allows matter to exist and where the universe refuses. They show where the known laws of physics hold and where those laws begin to crack. Imagine floating far from a neutron star, not close enough to feel its pull, but close enough to sense its presence. The star does nothing, yet space-time around it curves. Your body is not pulled toward it. Instead, space itself slopes beneath you. Time runs slower near the star. Clocks tick differently depending on altitude. Time dilation is not a theory, it is a measurable fact. Experiments on Earth have shown that clocks placed just a few meters apart tick at different rates. Near a neutron star, the effect becomes extreme. 1 hour near the surface could equal many hours far away. Time stretches. Gravity wraps around the star like invisible scaffolding, guiding the path of every particle, every photon. The universe reveals that gravity is not a force, but geometry. This is where Einstein and quantum mechanics collide. Gravity curves space-time. Quantum physics rules particles. Neutron stars exist where both must be true. The star's mass curves space-time so severely that time slows. Yet inside the star, particles obey quantum rules, refusing to occupy identical states. These two frameworks normally coexist without conflict, but neutron stars force them into confrontation. General relativity says mass curves space-time. Quantum mechanics says neutrons resist compression. The neutron star balances those truths like a blade walking between worlds. Scientists build equations to describe the matter inside neutron stars. These are called equations of state. They describe how matter reacts under extreme pressure. They predict the density, temperature, and structure within the star. Each model relies on quantum mechanics and nuclear physics, and yet none of them can fully describe the deepest layers. Because the deeper we go inside a neutron star, the more gravity warps time, and the more quantum rules strain. At the edge of physics, knowledge becomes approximation. The star becomes silent. Even our observations rely on guesswork. Telescopes like the Neutron Star Interior Composition Explorer measure pulsed X-rays coming from the surfaces of spinning neutron stars. By studying how light curves and stretches as it leaves the surface, scientists calculate the star's mass and radius. Each measurement refines the equation of state. Each discovery whispers secrets. Neutron stars refuse to reveal everything at once. That is why scientists watch mergers. They listen to gravitational waves. They observe kilonova explosions. These events give us data no laboratory could ever produce. The collision of two neutron stars shows what matter becomes when quantum rules and gravity finally lose the ability to coexist. When the merger forms a black hole, information disappears behind the event horizon. Quantum mechanics demands that information must be preserved. General relativity says information can be lost forever. This conflict is not a minor misunderstanding. It is the deepest paradox in modern science. It is the reason physicists search for a deeper truth, something beyond relativity, beyond quantum mechanics, a single theory that unites the two. People call such ideas quantum gravity, string theory, loop theory, ADS-CFT. These are attempts to describe reality where our knowledge stops. Neutron stars live at that boundary. Imagine the universe as a map. Most of the map is charted. Ordinary stars, planets, gas clouds, black holes. But neutron stars occupy the edge of the map. Beyond them is the unexplored. Beyond them is the place where equations break and physics hesitates. If you could walk along the boundary and look across it, you would see a place where space-time folds into itself. You would see quantum rules struggling against geometry. You would see matter choosing its final shape and surrendering to collapse. Neutron stars prove that the universe is not random. It is precise. It is structured. It has limits. It pushes matter to the threshold and then draws a line. This far, no further. Everything humans are made of would collapse instantly at the surface of a neutron star. And yet, out of that collapse comes gold, platinum, uranium, the ingredients for technology and art, the materials that shape civilization. Gravity does not only destroy, it creates. Neutron stars show us that creation and destruction are siblings. They show us that even death feeds the universe. They show us that matter is temporary, but transformation is eternal. And in the silence of a star that should not exist, the universe whispers the truth. The laws of physics are not barriers. They are invitations. Invitations to understand more, to push farther, to ask what lies beyond. Neutron stars are not the end of physics. They are where our understanding ends and where discovery begins.